Last time we started talking about vectors and some like mathematical preliminaries. Well, we almost finished talking about that stuff. There was one part that we didn't get to. We talked about how to do unit vectors using cosine and sine if you know an angle from a reference. Um, but we didn't talk about how to calculate a unit vector given 2 points. Like say you know that a vector is pointing in the direction from these coordinates to these coordinates. How do you represent that as a unit vector? So I had that as like the second way that we'll calculate unit vectors. That is a unit vector pointing in the direction of, there's got to be a better way to say this, but unit vector pointing in the direction of a vector between 2 points. Okay, so that makes it sound like, why would you want to do this, you know? But this is going to be a really useful thing, and I'll give a couple examples that show why. So this is basically what you use anytime you're calculating a unit vector in 3D, except in very unusual circumstances, or if you know coordinates instead of knowing an angle. Okay, well, the idea that we're going to use here is a unit vector v in the direction of a vector v is 1 over the length of the vector v times the vector v. And last time we talked about how to calculate the length. So for example, if the vector v is represented by these coordinates, then v hat, the unit vector, is 1 over the square root of vx squared plus vy squared plus vz squared times the vector vx, vy, vz. And this is a scalar multiplied by a vector, so you could carry that multiplication through to each of those components. And we're going to use unit vectors a lot. So unit vectors will be important to us whenever we have a force with a known direction but an unknown magnitude. And that's going to happen pretty often. And actually, it's not just forces. When we start talking about rigid bodies, this will be true of moments too, so it's really any load. And so the way that works is you can break up, so here's an example of when this would be useful. So using a unit vector in statics. Let's say that We have a bar connected to a pin joint at the wall, and we haven't talked about joints or anything yet, but you can probably at least believe the stuff that I'm going to tell you about the forces and stuff. So over here, let's say that this edge of the bar is connected to a cable. The location of this end of the cable is 2.51, say that's in meters. And the location of this end of the cable is 4.52. And we want to calculate the force vector applied to the bar by the cable. Well, we know that a cable, if you're approximating it as a weightless cable, all it can do is apply forces along the line of the cable and away from the body. So we know that this force vector, like we know its direction, we know it's pointed away from this connection point towards this connection point, okay? And we have the coordinates of these two connection points. So we can come up with a unit vector pointing in this direction. We don't have any information about what the magnitude is yet, but we can represent this force vector as the tension in the cable, the magnitude of that force, times the unit vector, okay? And that unit vector, we're going to calculate this way. So first calculate a displacement in the right direction, okay? So this would be 4.52 minus the starting point of that vector, 2.51. And so a vector that's in the same direction as our unit vector is going to be 2, 1. Okay, but that's not a unit vector. That's just a vector, and the magnitude of this has no meaning to us at all, right? All we care about is the direction of this, because that's the same direction as the force. So now we're going to calculate the unit vector by doing 1 over 2 squared plus 1 squared square root times the vector. And you get a value of 2 over root 5, 1 over root 5. Okay, so now the force vector is, you can think of it as this variable t times this number. So we have 2 times the square root of 5 t for the x component, and 1 times the square root of 5 t for the y component. What was the benefit that we got from doing this? Say it again. Yeah, so it has to do with, it has to do with the balance of variables and equations. All of our problems are going to end up being a system of equations for some number of variables. And if you don't have enough equations for the number of variables you have, then you can't solve it. So what we've done here is, instead of treating this as an unknown force vector that would have 2 variables associated with it, an x component and a y component, through all this, we came up with a vector with only represented by a single variable, okay? So the benefit of using this unit vector idea is, when we don't know the magnitude, but we do know the direction, our vector has only a single variable instead of 2 variables in 2D or 3 variables in 3D, okay? So we represented this unknown vector using only one variable. Any questions about that? Okay. So now we can go on to statics of particles. So first, a particle is an object with mass that's assumed to have no length dimensions. So we treat it as if it just is at a single point in space. Since there's no length dimensions, there's no distinction between a left and a right or a top and a bottom. It's just a single point. Therefore, we don't worry about the orientation of particles. So we don't worry about particle orientation. We only worry about its location. So let's say Newton's equations of motion are, first, Newton's second law is sum of the forces is equal to the mass times the acceleration vector. And in fact, you know, if you have a arbitrary object and it's spinning, moving through space, obviously the acceleration at one point isn't the same as the acceleration of another point in general. So what's the point that matters for Newton's second law? Like this can only hold, this can't hold for every point if something's spinning, say. Center of mass, yep, that's right. And the rotational equation of motion, what I call rotational Newton's second law, because you can derive it from Newton's second law, says add up all the moments about some point A. Those have to equal the moment of inertia about that point A times the angular acceleration vector, which doesn't have any about point or anything. This is a trickier question. This is really more, this isn't going to come up in statics, but leading towards dynamics, because a lot of you are going to be taking dynamics. Anybody know what the restrictions are on what this point A is? You might think this could hold for any point, but that's not true in general. Anybody? The center of mass, well, the center of rotation, yes, and the center of mass. So this holds for a fixed point, like a place where the object is, say, connected by a pin joint or something to the ground, to the coordinate system, or where A is, so A is a fixed point, or A is the center of mass. By the way, when we get to this, the reason that we don't have to worry about this is because since this is static, every point in the universe is, you know, the center of rotation, like you called it, is a fixed point on the body. And so we can put our about points anywhere in statics, but in general, you can't do that. Okay, so Newton's equations of motion in 2D give us two equations here, right? Because you have two-dimensional force vectors, two-dimensional acceleration. Somebody brought up yesterday that when you have a cross product, so moments are cross products, and when you take a cross product between two things that only exist in the x and y, along the x and y axes, the result is only in the z axis. So in 2D, this only has a z component, okay? So in 2D anyways, this is two equations, one equation. In 3D, this is three equations, three equations. If we're just talking about particles, this goes away. So this goes away for particle statics because we're not dealing with changes in orientation. And so we're just left with Newton's second law. So we have two equations in 2D from Newton's second law and three equations in 3D from Newton's second law. For the static case, the acceleration of the center of mass is equal to 0. So the equations that we have to deal with are add up all the forces on the particle, and they have to add up to 0, a 0 vector. One thing to notice about this, most of the problems we'll deal with, objects will be fixed in our coordinate system, but notice that this also is valid for anything with a constant velocity. As long as the acceleration is 0, this equation holds. Okay, so if you have a problem where like a car or something is moving with a constant velocity, you can use the equations of statics in that case too. So notice the sum of forces is equal to 0 holds for particles with constant velocity vectors. Two. In this class, every time you use Newton's second law and or the rotational Newton's second law, you have to have a free body diagram associated with it. I'm going to just always abbreviate that as FBD. And And so I want to just give you some requirements for the free body diagrams that you draw. This to me is a really important part of this class. So I'm not very flexible on this, you know, especially in a class early in your engineering. You know, you haven't been doing this kind of analysis for a long time. So if you come to me and say like, well, I have this other way I like doing, you know, like, okay, change it to this way. I'm glad you're happy, but change it to this way. Okay, so here's what I expect in your free body diagrams. So choose a body or a piece of a body to isolate. And then draw a closed outline of that body. Okay, so say that we're doing a free body diagram of a car, okay? And the car is sitting on the grass, you know. And a cat is sitting on the car. That's probably good enough detail on the cat. And, you know, I don't know. The wind is blowing. So you have to choose what you're isolating, and all that you put in your free body diagram is the thing that you're isolating. So if we're isolating the car, the free body diagram needs to start with a closed outline of the car like that. And you don't draw the cat or the grass or the wind, okay? It's just a closed outline where inside the closed outline, everything that's happening is internal, and outside, everything is external, okay? The whole point of the free body diagram, besides sort of bookkeeping, is just breaking up the world into internal forces and external forces, okay? And that's why I want you to draw this outline. So don't do this. So what's the problem with this picture? Yeah, I put the grass in. So it's like, well, then there's sort of this this gray area in here. Like, what about forces on the grass? Is that part of this, or is it not part of it, you know? And don't do, with a car, this would be a little odd, I suppose, but I don't know. Don't do something like that. Like, what's the problem with this? That's not a closed outline. So the closed outline just makes it really easy for you to be clear to yourself about what's internal forces and what's external forces. This, it's not so clear, you know, because, well, why? Yeah, well, it's just like, yeah, it's like representing something with volume by something that doesn't have any volume. So you don't know like where this line is. Is that the line that represents the bottom of the car? You know, is that the line that represents the top? So do it as a closed outline like this. No, the cats, that's not a big, you don't have to do any calculations involving cats this whole semester, in fact. I'm pretty sure that's the case. Maybe on a problem set, but not on a test. I'm just trying to think through all the practice problems. I don't think there's any cats on any of them. So I wouldn't spring that on you on a test. Okay, so now the third step is draw all the loads that are applied to the chosen body, to chosen body by external objects. These all fit into two categories. This is, it's kind of surprising that it's this simple, but these are the only kind of forces that we're gonna, and only kind of loads that we're gonna deal with in this class. That's just the weight, so the force applied by gravity, and then contact forces or contact loads applied by objects that are touching the boundary. So in a really, when a problem gets really complicated, there's a lot of points where there's contact and stuff. This is something you can sort of, center yourself with. Like, just remind yourself, well, there's going to be weight. So put that in there. And then just look for all the points where external objects are touching the boundary, that you drew for your free body diagram. Wherever there is contact, there's going to be a load. And wherever there's not contact, there's not going to be. Okay. Here's something, sort of a slightly subtle thing. The Newton's second law version that we're using, and Newton's second law in general, says add up all the forces on the body and, whatever. Then the law says what that sum is equal to. In step 3 here, I didn't say draw all of the loads that are applied on the body. I said all the loads applied by external objects. So what about all those? I mean, if you think about an object being billions of atoms, each atom feels forces applied by other atoms that are still internal, and you can imagine what a horrific mess it would be to do calculations if you had to account for all of those internal loads. So how did I get to take this sort of obviously it's pretty clear why we want to take the step of only dealing with external loads, but why can we throw out all those internal loads? Well, that's true, but that is true. This is going to be generally the case though too. So when we talk about rigid bodies, we're going to be able to throw away all those internal loads too. So that is a little surprising. When we talk about Newton's third law, it'll be clear why that is. Okay. But so we've already taken the big step of going from all the forces acting on a body, all the loads acting on a body, to all the external loads acting on a body. And basically by doing that, we've made it possible to do any calculations at all, Okay, so the loads applied by external objects all fall into two categories. first, loads with known directions. And second, loads with no known direction, unknown direction. For the first one, if the direction is known, you're going to represent the load with an arrow in the known direction, and associate that arrow with a scalar variable. So for example, if this is the free body and you know that there's a force going up and to the right, then you'll represent that force like this with a scalar variable t or f or r or whatever. So what's the thinking here? Do you have a feel for that? Why are we representing this with just a single scalar variable? That might be a dumb question, but it has to do with that unit vector thing that we just talked about. If we know the direction, we know we can break up a force vector into a scalar magnitude multiplied by a numerical unit vector. Okay, and so this represents, this is the only unknown we have, is the magnitude of that vector if we know the direction. Okay, if we don't know the direction, then we don't know anything about any of the components. So if the direction is unknown, then we're going to represent the load with a little coordinate system. And we're going to associate that. So the little coordinate system just says we have a component this way and a component this way, and in 3D we also have it this other way. We're going to associate that coordinate system with a vector variable. So for example, if this is the free body and we have a force acting on it, but we don't know the direction, wherever it's acting, you draw the coordinate axes like that and associate it with a vector variable. And what that says is we have two unknowns here in 2D, or if we're in 3D, we have three unknowns. There's no way to represent this with fewer variables than a fully unknown vector. Okay. Okay, so let's do an example using this. So let's say there's a wall there, and a mass is hanging from two cables. And let's say that this connection point is -2, 1. The units I'm going to use are always SI units. So if I ever, forget to give units, any length or distance or coordinates, I'm talking about meters. Any forces, I'm talking about newtons. Okay. Any masses, I'm talking about kilograms. And this point over here is +2, 1. and this mass is 10 kilograms. And let's say that we want to figure out what are the cable tensions. The way we're going to do this is use Newton's second law, and that means we need a free body diagram. So free body diagram, I'm going to isolate the 10 kilogram mass. So a closed outline is this, and I'm not drawing any external things. So what forces are acting? There are the two tensions, and then the weight. Yep. And so I'm going to just first draw the weight in there. That force is going to be 10 kilograms times 9.81 meters per second squared, so 98.1 newtons down. And now we just have to mentally go around the boundary looking for places where there's contact. And the only places where there's contact are where the two cables are attached. Do we know the directions, or is that an unknown direction of those forces? Actually, it is unknown, but if I give you this, which I meant to, then it's known. So we'll say that this mass is at the origin. Okay, so we know that the forces are acting along the cables, away from the chosen body. And so these are both known directions, unknown magnitude though. So there's going to be one force going this way and one force going this way. I guess I'll call the one on the left T1 and the one on the left T2, on the right T2. Any questions about the free body diagram? Okay, and so now we're done with this, and now we can go on to Newton's second law. This free body diagram just right off the bat says we only need two variables to represent this. But in order to do it mathematically, we need to come up with the unit vectors for these two. So the unit vector for that cable 1 on the left is, well, let's say, so I'll get first I'll come up with a vector that goes from the mass to this point. Okay, that's just like a displacement. So that's going to be -2, 1, -0, 0. So -2, +1. And now we need to make that a unit vector. So the unit vector is 1 over square root of 5 times -2, +1. And you get -0.894, +0.447. Okay. And then, so this is the unit vector for cable 1. I guess I'll name these both subscript 1. And then subscript 2, the vector going to the point 2, 1 from the origin is +2, 1, -0, 0. So you get +2, 1. And then the unit vector is 1 over √5 times +2, 1. So you get +0.894, +0.447. And now, if you use these in Newton's second law, you get -0.894 positive 0.447 times the scalar variable t1. So if you multiply that, you're going to get this in both positions. You're just multiplying that unit vector by a scalar. And then plus positive 0.894 t2, positive 0.447 t2. And then the last one is this weight force. I've been using like a standard coordinate system here. And so this is going to be in the negative y direction. So we have to add that on. 0, negative 98.1. And these are equal to zeros. Okay, so now we have a system of two equations for two variables, t1 and t2. The first equation says 0.894 t1 is equal to 0.894 t2. So t1 is equal to t2. And so substitute one of those in, to the second equation. And you get an equation that says 0.8, what's that? Oh, that's 894. So 0.894 T1 is equal to 98.1. And so T1 is equal to 109.73 newtons. And then that's also equal to T2. Yeah, that's the magnitude. That is the magnitude of this vector. And so now if you want to find it as a force vector, now you just multiply that times the unit vector, and you come up with a force vector that's applied to the body by the cable. So the force F1 is equal to 109.73 times the unit vector negative 0.894 positive 0.447. Could someone calculate that? I don't have that. And then the force vector F2 is going to be 109.73 times the other unit vector. Oh, this is going to be okay. Okay, thanks. And so this one then is positive 98.1, positive 49.05. So notice that every force that appears in Newton's second law appears in the free body diagram, and vice versa. Every force that appears in the free body diagram appears in Newton's second law. If you don't have that, then there's no point in doing the free body diagram. You know what I mean? Like, that's the whole point of the free body diagram. And doing it right is going to help you in this class but also in deform and dynamics and everything. And that's why in this class, I'm really going to focus on this. Yep.
I remember in physics, this is kind of like a nitpicky thing, but whenever we had tensions,
Mhm.
we had to draw like the stumps.
Oh, yeah. Well, sometimes that helps on complicated problems to think. I can't remember if you don't have to do that, but sometimes, yeah, I find that it sometimes helps people if you're having trouble with complicated cable tension problems to include just a little bit of the cable in your isolated free body. So you have little stumps of the cable on there. And then your cable force is going straight out of the stump, like perpendicular out of the stump. In this problem, it's pretty easy to figure out what direction it's going, but these cable problems can be a little confusing in cases where you have like an object that's being held up by I have that backwards. Okay, so say that you have one cable going around all these pulleys and somebody's lifting this mass by pulling this cable through this system of pulleys. Then it can start to get you turned around backwards a little bit on what direction the forces are going. And that's when sometimes I think it can help in your free body diagram to include a little piece of that cable. And it just tells you exactly what direction the cable forces are going. Yep.
I noticed in the practice problem, there's only like 10
Uh-huh.
kind of these kind of things.
Yeah.
Is there additional?
No, that's all the problems there are. I would so I'd say first of all, when you're going through the practice problems, go through them pretty like. So first, go through them more than once. You know, like if you know those really well, then you're going to be really ready for the test. You know, and second, every time you go through them really consciously. Just like ask yourself at each step, because you don't want to be just memorizing those problems. You want to think like, okay, why is this direction this way? Why is this? How do we know the direction for this one, but we don't know the direction for this one? You know, and I think you'll find if you go through them in that way, it's plenty of work to do. And then also the example problems are more problems. You know, like the ones that I'm doing in class. If you have time, go through and try to work through those too. You know, because those are usually trying to get a specific point across. You know. Any other questions? Yep.
The 3-point given problem, was that just points?
Yeah. Right. Yeah, what I gave you here are the coordinates of those 3 points. Yep. Yep. Any other questions? Okay. Let's take a 10-minute break, come back at 2:02, and we'll keep going.